So I'm gonna talk about DRAM today. That is memory cell for the memory RAM memory in the normal PCs. That also showing normal residence, like it's not just some server thing. So every PC have some memory cells. Usually the difference is mostly in the size. So some PCs have 16 gigabits of RAM, 32, or even 64 for high-end PCs. But let's start with the actual bit memory system architecture. I already told about the SRAM, and I think it's enoughly clarified. But I'm going to talk to you about the DRAM right now. So let's go. This is the setup for DRAM. It's really simple. We have a capacitor here, one transistor, and that's all. We have the ground connected here, some VDD, half a VDD in word line and half the VDD in bit line. VDD stands for the high, so 1 volt for the that case. And that's all. It's like one capacitor and one transistor. You can just see in this way. So about the actual group of DRAMs, you can imagine like some rows connected by the word line and columns connected by the bit lines like that. In the end of the column will be a sense amplifier, and after the sense amplifier, like the output bus for read situations. For write situations, we don't use the actual output bus, but we use the bit line that comes from other place from the processor. Also, the output bus can be seen as multiplexers, I think, but I'm not sure about the part, so let's just keep in the cells. So here, when the actual cell have some state, for example, the bit line stands for 1 here, 0 here, and 1 here, or 1, 0, 1. Because this bits, this cell is made of capacitor and transistor, we have some leaks, so it's not definitive, and we have to keep refreshing the DRAM. This is the most like downside of the DRAM compared to the SRAM, but we have a more denser system because the DRAM is really smaller. It's just one capacitor and one transistor, while the SRAM have six transistors at least. I mean, there is the four transistor too, but it's not that used. So six transistor is the baseline for industry. The DRAM is also slower because of its refresh and also the distance from the processor. But okay, getting back here. 1 volt, 0 volt, and 1 volt, 1 0 1. It is time to, it becomes degrade, like the charge or the capacitor leaks and the transistor also leaks, so it becomes, it's not eternal. We have to refresh this data. So we're going to actually turn on the bit line here with half the VDD. So for our case, that is didactics, 0.5 volts. So if this, I'm going to explain why, but half the VDD for all the bit lines, then we turn on the word line. So the word line, because of this transistor, you connect the capacitor that is charged or not charged for 0 or 1, and we're going to enter in contact with the beta line that is half VDD. So if this capacitor starts 1 volt, the VDD will be up. Even if the 1 volt is a bit degraded for 0.9 or 0.8, the bit line will actually increase because it started with half the VDD or 0.5 in our case. So if it's 0.8, and the VDD is zero point 0.5, the VDD goes up for 0.6, 0.7, while the capacitor will, in the bit inside, will degrade for 0.6 or 0.7 too. So now we have a new station where the bit line will be like 0.6 or 0.7, while the capacitor will also be that. For the one here in that was 0 volt, the VDD that started with zero point 0.5 will actually go down for 0.3, for example, and the T 0.1 will also increase to 0.3. Then what happens here? The sense amplifier will, based on this difference, like from 0.5 to 1 or 0.5 to 0, it will actually amplify for one side, for one of these two extreme situations, right? So this one will take the bit line to 1, this one to 0, and this one to 1. So if the bit line goes to the extreme and the word line is actually activated, we also charge the cell for the original value. So we can think that as the refresh, because we got the value, changed the bit line, the sense amplifier got the value back to the original, like the complete value without the degradation of the bit, the charge, and we actually refreshed the bit lines, the memory cell. So these three memory cell will be refreshed at the same time because we do this at the row level. It's important to say that these DRAM cells have to be refreshing, I think, in 64 milliseconds, but one cell have to be refreshed at every 64 milliseconds. But if you think it is updated by row, and all rows have to be updated, and you can just update two rows at the same time because the bit line for this is different from the bit line for the row from the below and from below, for example, this one. So we have to do at the row level. So we do this at the row and then do this and go for all the rows. And in 64 milliseconds, we have to get back to the same row. I think for the example I wrote in the blog post, the updates was at 7 microseconds and nanoseconds, something like that. So we run one refresh every 7 microseconds or nanoseconds. I don't remember. And that's it for the DRAM. That is not that hard because the refresh is actually a read and write operation. So if you think that you just want to read, you just have to open the word line and the bit line, then the sense amplifier will amplify the value, and in the output you, there is a decoder here too, but the output bus will get the data. So even if it's refreshed, we don't need to refresh in this case. We just want to read the data, which is okay. For the write, it will come from upside. So the bit line writes some value. Actually, the bit line stands with some charge, and this charge the actual DRAM cell, and the data is wrote. So it's simple. The refresh part is actually the most complex part, I think. But even this is not that hard. I think the SRAM cell is more complex than the DRAM. But that's all. I think for SRAM is this.